everyone, it's Alyssa. In this video, I'll be breaking down the aqueduct generation system. The aqueducts are made in two steps. First, I use my wall generator HDA to model the wall modules that'll make up the aqueduct. Then, I assemble them using a second aqueduct generator HDA. This makes it easy to generate many different variations, or plug in your own models. It's also handy having the wall generator separated from the assembly because I can reuse the wall generators for the towers and buildings. Now I'll dive into each tool to give an overview of how it works and highlight points of interest. First, I'll start with the wall generator tool. The wall generator creates four main features. The first is the actual surface of the wall. The next is the windows, the pillars, and then the decorative arches. I'm going to open another parameter tab and pin the settings for this wall generator so we can access them when we're inside the network. And now let's dive in. So the base of each wall is this grid right here, and the size is controlled by these settings, of course. And that base wall feeds into different sections that create each feature of the wall. And these are roughly laid out corresponding to this menu. So first is the top rail and the overall wall surface and window shape. Then are the pillars, and then lastly the decorative arches. Now I'm going to walk through this network starting on the left and working my way to the right. So the first part of this is, let me just show the wall, this top rail. It's very simple. It just starts from the wall base, extracts the top, and sweeps along it. But I have two options, one to create a round top rail and the other to create one that's more square. And this is for the building walls so that I can make these things that kind of look like wooden beams on top of each wall. The one thing is, even though the sweep node can create UVs, by beveling it, it kind of will destroy the UVs. And so I use the Labs Auto UV node in order to make new UVs. So you can see the Labs Auto UV node automatically lays out the UVs, and if you go into here you can see they're pretty decent. So that's pretty much everything for the top rail. That part's very simple. And this next section creates the wall's main surface and the window. So this top part just creates the window shape. This switch switches between different window shape options. So if I go here, this menu is the one connected to the switch. Originally I had all these windows just driven by a custom curve, but I found that 99% of the time I just want a rounder arch, a sharper arch, or a rectangle, and so I built those in as default so the user doesn't have to be constantly adjusting the ramp every time they make a new wall. One little trick I use to keep this wall as low poly as possible is use the Labs alias remove inline points. So this is an alias to the facet node that sets it up so that it'll remove any inline points, exactly what it sounds like. So the reason I do this is because after I resample the shape of the wall, you'll notice that there's some places that are more curved where it does make sense to have this many points, but there are other places like down here where it's pretty flat, where there's really no reason to have that much geometry. We could just have like a point here and a point here, and it would be a lot lighter and we wouldn't lose any shape. So the remove inline points lets us do just that. So you specify a distance, and then any points that are in line under that distance will get removed. And now we have exactly what we want, where there are more points in the curved parts that need those points to maintain the shape, and fewer on the straight parts. And then I use the Symmetrize node to make it so I have both sides of the window. This node is similar to the mirror node, but a little different in that when you use the mirror node, if the shape that you're mirroring extends over the axis that you want to mirror over, when you mirror it, it just keeps the whole shape. But for the Symmetrize node, it'll clip off anything that goes over the axis, which is what we want in the case of making these windows. And then I just turn this path into a closed shape, and I also do this last little operation on it to handle an edge case. So let me visualize the whole wall. Basically, if the window goes outside of the region of the wall, either by being positioned too high or by being scaled so that it extends beyond that region, I don't want the wall to just like have an extra bit of window sticking up at the top. I want the window to get cropped so it fits within the wall. So I do that using this box clip node. And I could do this with a Boolean, but Booleans are pretty slow. And so instead, by clipping, this runs a lot faster. But I don't want to have to chain a bunch of different clips to take care of every single axis for each bound of the wall. So instead, I can use the Labs box clip node. How this works is it takes in an optional bounding box, as well as the shape that you want to clip. And if I move this up a little more, you can see that this is clipping everything on this window that goes outside of this bounding box. And I'm able to specify along which axes I want to clip it. So if I unchecked this, then it would leave the positive Y direction alone. Of course, I do want that checked, but that means that I can uncheck these Z directions, because if I had these checked, because this is completely flat, then it would just always get rid of it. So this is a handy way to clean up my window so it's not going to break any rules. Next, this window shape feeds into these two branches, where this left one creates the window itself with another HDA, and this right one creates the wall surface. So let's start with this wall surface. Again, you could do this by just booleaning the window out of the wall, but one, that's pretty slow, and two, that'll leave you with some not so nice topology where this entire front face is just one polygon. And so instead I use my own method to create this, which is faster and leaves me with quads. So the way I do that is I take each point and I project it out against the shape of the wall. So I first extrude the path so I get those additional points that I want to project, and I group the points that I want to project based on the seam from the extrude. I set a direction from the point it came from to itself using a little bit of vex in the near points function, and then I blur out that direction a little bit, I'll show why in a second, and I ray those out. Now you'll notice we don't have the nice square corners we want, so I have a little more vex that snaps those corners in place, as well as some more nodes to handle tricky geometry. So quickly explain what the blurring and these other things are for. Basically, I was running into an issue where if I have a sort of more strangely shaped window that curves in on itself, then if I don't blur the directions to project it out, I get this like horrible geometry that intersects itself, which makes sense because it's like going in the direction out from the shape. But because the shape is concave, the edges intersect themselves. So instead, by blurring out the direction they get projected in, I kind of relax these directions a bit and I avoid that problem. I was also having another problem where after these points are rayed out, even after blurring these, they would still intersect each other a little bit. And so the way I fixed that was by using the labs group by measure node. At the moment, the group by measure node just has one setting, but this could potentially be extended in the future, and that is group by eccentricity. So eccentricity is essentially how square a shape is. So if it's very long and skinny, it's going to get grouped by this, which is exactly what we want. So it's going to group these long and skinny bits, which are the ones causing our problems. And that lets me then promote that group to points and then fuse those points together. And that cleans up the geometry quite nicely. And then I just snap to the corners, just using some vex. It's mostly just near points. And then I'm done. I have this extra clip node to deal with some occasionally slightly messy geometry that comes out. And then that creates the surface for the wall. So I just thicken that using the labs thicken node, which is sort of similar to extruding, but it has this nice setting I like to extrude in both directions, which is nice if you want something that's centered at its original spot. And again, I auto UV the walls. So here are the walls, automatic UVs. I don't really care about these overlaps because they're behind the windows, but if I did, there's another labs saw called labs UV remove overlap, and that'll move apart any overlapping UVs. Now, you might not want this because it doesn't create the cleanest thing, but sometimes I do like to use this as a check to see whether I'm getting overlapping UVs. So in that case, this create group from detected overlaps is really handy because I can just plop this node down, see if anything ends up in the group, and if so, I know that I have overlaps. One other useful UV-related labs tool is labs calculate UV distortion. So it calculates and also visualizes UV distortion. So in this case, I don't have a lot of UV distortion, but in this other UVing option I have, where the UVs just get projected straight onto the plane, which I do for the building walls, and I'll explain more about that in the building video, then you'll notice if I plug these UVs into here, it does show that I've got a lot of distortion on those. So this is a handy node if you want to check the quality of your UVs. Next, I'll go over how this window base shape turns into an actual window. So basically, the window has two main parts, the frame and the pattern, which has this grid lattice, a repeated shape, and this top pattern. So the windows are generated in this HDA. I turned it into an HDA because it's also used in a couple other places, like for the building roofs and dormers. But if we dive in, essentially this part creates the frame. This part is the window glass. This is the main window pattern, so the lattice and the repeated shape. And this is the top part of the window pattern. So starting with the window outline, for a shape like this, you could just plug it straight into the sweep node, but because I want the window generator to work with any arbitrary inputted shape, I want to sanitize this input a little bit and just get this outer edge to sweep. Luckily, Labs has a node for that, so using the Labs extract borders node, I can just get that in one node, and then I sweep it. I also have an option to get rid of the bottom edge, because in some cases, like for example, if you use the wall generator to make an arch for the aqueduct, and this window is really a big arch cut out of the whole wall, you don't want a bar at the bottom. I do that by grouping this bottom edge and then using Labs edge group to curve to get rid of the bottom edge. I believe that as of Houdini 20, the convert line swap has absorbed all the functionality of this node, so this node might get deprecated soon. But any place I use this, you can just use the convert line swap. Next is the window glass, which I just make by taking that base shape and using the thicken node, and then there is the main window pattern. So at a high level, the way this works is I take a grid and then I fit the grid to the window shape, and then I copy the repeated shape onto the points of this grid, like so. And I also use that grid to create the inner framework. And then I merge those together to get this pattern. So overall, this is pretty simple, but I want to point out a couple handy Labs nodes that made this really easy to do. First is the Labs simple shapes node, which does exactly what it sounds like. It can generate simple shapes. And so it's great for if you just want to make a quad or any n-gon or stars. So yeah, it's a really great node for if you're making geometric patterns like these. Then after that shape is copied to the points, you'll notice it extends outside the bounds of the window, which is not what we want. And we could just do normal geometry Boolean, but what is actually a lot faster is Booleaning curves. So what we can do is extract these curves and then use the Labs Boolean curve node to get just the parts inside the window. So on the left side, I have the curves to Boolean, and then on the right side, I've thickened the window shape and plugged that in, and now I get only the curves inside the window. And then lastly, depending on what shape you have inputted into this thing, Boolean might leave you with these little bits that you don't really want. So I use the Labs delete small parts node, which deletes anything that is below the specified threshold to clean the geometry up a little bit. And then to create this lattice from the original grid, I want to create the lattice on these interior edges, but I don't want it to go around the outside because that is already taken care of by the frame, and it's going to create kind of messy geometry if I just plug this whole thing into a polywire. So what I do is I use Labs fast group unshared to group the unshared edges, which are going to be on the border of this geometry. You can do the same thing with a group node, but you have to fiddle with some settings, and also this node runs a lot faster. I can then just extract the non-unshared, so the shared edges, and then I resample those and polywire them to get our little lattice. And then I merge them all together, fix the funky normals, and then I have the main window pattern. And lastly, this section generates the top pattern of the window. So first, this clip isolates the top of the window depending on where the user specifies it should be clipped. And then this left box generates the radial lines, the middle one creates the arch in the center, and the one on the right creates the bottom bar. Just a couple things to point out in here. Again, we use Labs fast group unshared to isolate the edges that we don't want for making the spokes, and then take the other ones. And then again, use Labs curve Boolean to isolate the parts of the spokes we want and optionally cut out the center. For the arc in the center, again, we start with Labs simple shapes and use remove inline points to get rid of any unnecessary points, and then turn that into curves and sweep it. And all of that makes this top pattern. This all comes together to make the window. Note that the window frame and pattern are a separate output from the window glass so that it's easy to apply different materials and groups onto them. All right, now that we've gone through the window generator, I'm going to pop back up to the wall generator and talk about how it creates these pillars. So these pillars are very simple. They are just cylinders with these little shapes on the top and bottom. So the left part creates the pillar base by taking a curve and revolving it, and then copying it to the right positions. And the right side just creates the cylinder, and they get merged together. The only interesting thing here is the Labs UV Unwrap cylinder node, which will automatically UV a cylinder. So you can see here, the cylinder has been UV unwrapped. This is the body of it. And then there are the end caps. And it even works on things like the base, which is like not strictly a cylinder, but because it has the same sort of topology as a cylinder, it also does a very good job UV unwrapping that. When I place these pillars, I make sure that they're oriented so that the UV seam is going to be on the inside facing the wall so you won't see it. And the way I check that that's the case is I use the lab's Visualize UVs node. So if you plug in any texture, this Visualize UVs will preview that texture on the geometry. And you can see here that the seam is in fact on the inside of the pillar. So those are the pillars. And the last thing is the decorative arches. So essentially the arches are made by taking source points along a line like this, and then copying curves onto that line and then mirroring it. By changing where the source points are and changing things like the bend and scale of the curves that get copied onto them, you can get some pretty nice variations. So at a high level, how this works is I have two options for the line that the source points can come from. It can be either from a horizontal line or a vertical line, and there are options to change where it starts and how long it is, as well as change how that curve is resampled. So the distribution of points along that line can be controlled with a ramp, and that is done by using the lab's curve resample by density node. So this ramp just references into here, and you can see that the ramp is driving how these points get resampled along the line. Then this curve just gets copied to those points, and you can also control things like the scale of the lines along the curve. I use Boolean curve to keep the arches inside the wall, and then I remove inline points to get rid of unnecessary geometry, and then I mirror them. I also have the option to add a spiral to this pattern. So if I click add spiral piece, that plugs into this switch, and then there are just some settings for placing the spiral. To create the spiral, I use the lab's spiral node. There's also another spiral node built into Houdini, but let me drop that down to show the difference. That spiral node kind of makes these very concentric loops, and the lab spiral node makes a golden ratio spiral. So for things like this, I think the lab spiral node fits this kind of design very well. Then on the right side, this part creates a centerpiece that can be added to the arches. This is very simple. It's pretty much just starts with a shape that gets positioned and polywired. Optionally, a circle is added around the shape. This gets Booleaned out from the arches using the Boolean curve, and then it all gets merged together. One thing I want to point out is these shape options are all from the lab's Superformula shapes node. It's a bit different from the simple shapes node because these are all a specific set of mathematically defined shapes. So you can see they're pretty fun settings on here, like you can make flowers and clovers and things like an eye shape or a teardrop shape. So this node is really nice for creating a bunch of options for these sorts of designs. And I have these giant switch with different Superformula shapes with different settings so that the user doesn't have to drop down more nodes, but an easy way to use this tool would be to use this input to plug in the shape you want to be on this arch, and then you could set whatever settings on the Superformula shape that you want to put any shape in there. After this is all merged together, I use the box clip node just like I did with the window so that these arches get clipped to be only inside the area of the wall. And I also have an option for if you didn't want these rounded arch shapes and you want a flat extrusion from the wall, I use the lab's extract silhouette node to get this flat silhouetted surface, and then I extrude it to give that flat pattern. And that is pretty much the entire wall generator. The only two little things left to point out are, one, these group nodes I have at the end of every chain, and these are just so that the user can assign groups to the different materials coming out of this node, and then those groups can be used later for shading. So all the groups have this postfix so that it's easy to specify in other tools not to delete these groups, and then they have a unique prefix. So the wall will have this, everything made of glass will have this. The window frames and the decorative arch, I've both set to this metal prefix because I want them both to be made of metal. So those groups are just to help me out down the line. And then the other thing I wanted to point out is when I place this wall later, I'm going to want to align the edge of this wall, not the edge of the pillar, to other walls. And so I merge in this bounding box that only contains that part of the wall so that later for wall placement I can use this bounding box instead of the wall itself in order to align them correctly. And I color the bounding box magenta just so it's really easy to tell what it is and I don't ever get confused like, what's this extra geometry hanging around? But because it's kind of annoying to have this bright magenta box, and also for some of the other modules, the module isn't an exact box shape, so the bounding box actually kind of obscures what's going on, I have this option to preview with invisible bounding box, which is plugged into this switch. And what this does is it just sets the alpha of the bounding box to 0 so that you don't see it. So now that we've talked about how the wall generator works, we can look at using that wall generator to create aqueducts. So I've already created a couple wall variations using the wall generator, and I've assigned all of these a module ID attribute. The aqueduct tool, as well as the tower and buildings tool, use a module ID attribute to tell the different modules apart from each other. I like to set the module ID using an attribute create instead of on the wall generator itself, so that the workflow is the same whether you're using the wall generator or plugging in your own modules. I also found that if I build the module ID into the wall generator, then I just forget to set it, but if it's a separate node that I have to put down, that makes sure that I actually set a unique module ID for each module, avoiding any problems down the line. So I merge all these wall modules and I plug them into the left input of the aqueduct generator, and then on the right I give the aqueduct generator the curve that I want to base the aqueduct on. And you can see that the generator places walls along the curve. So if I edit this curve, the module generator will adapt accordingly. So this first setting is the module pattern. Remember, the input modules we plugged in have ID 0, 1, 2, and 3. And right now, because the module pattern is set to 0, it's using module 0. But if we wanted, we could plug in 2, and then it would use module 2. You can also specify multiple modules in a pattern, and it'll do that. So if we want to alternate modules 1 and 2, then we just type 1 space 2, and then we get modules 1 and 2. There's also an option to flip the geometry, because there's no real way to know what the right side of the curve is, so I just hand that control over to the artist. And there are also some scaling options. Right now, the tool is just scaling the modules to match the target height of 20. So that means that even if I have two very different height modules plugged in, so if we give it 1 and 3, you can see that module 1 is pretty short, module 3 is quite tall, but the tool adapts the module sizes so they match this height of 20. And to verify the height is 20, I'm going to use the lab ruler tool. So this is not a node, it's more of a utility, but if you type ruler in the tab menu, it'll activate it, and then in the viewport, you can drag along what you want to measure, and it'll measure the distance. So you can measure along anywhere you want, and it'll project the points that it's measuring onto the geometry. So that's a kind of silly example of using the ruler tool, but I find it's really useful when debugging. If, say, my modules are not getting placed or scaled the way I expect them to, I can use the ruler tool to check if their real heights or widths are what I expect, or if I'm getting something else, without having to go into the geometry spreadsheet or drop down any nodes. I also have another option on the scaling mode to use an explicit scale. So instead of matching a target height, I can explicitly specify the value I want each module to be scaled by. So this will not resize the modules to be the same height, and instead maintain the ratio of their heights to each other. Also, you'll notice that right now, because usually when the modules are tiling with each other, you don't want pillars on both sides because you'll get duplicate pillars. But if you have a case like this, then you might want both pillars. So on the wall generator, there is a setting to create a full tile, so that'll make pillars on both sides. Or maybe I could disable the pillar on this one if that's the look I want. So that is the curve input option. There is one other option, which is to input a blockout. So if I change this to blockout, it won't create anything because there's no blockout coming in right now, just curves. If I move these away, I have this very simple blockout here, which is just 2 boxes and 1 box is bent. If I plug this into the aqueduct tool, then it'll generate walls that match that blockout. So I'm noticing the walls are backwards, so that's what the flip geometry option is for. And now you'll notice that in blockout mode, there's another option, which is to disable these scaling modes and instead override the scale to match the blockout height. So you'll see if I template the blockout, these are now adhering to the height of the inputted blockout. So if I rescale this box, the height will match it. And same if I resize it, the wall is going to adapt accordingly. But if I want to use the other scale settings, I can just uncheck this and set those like normal. Now let's take a look at the inner workings of this tool. It's actually super simple. It's pretty much just a chain node with a little bit of extra logic. So the wall modules come in here, and the first step is to pack them. The reason I do this is the chain node is quite slow, and so if you give it complicated geometry, it gets slow pretty fast. So first I promote the module ID to be a primitive string attribute because you need to do that in order to pack geometry. And then in here, I split apart the different components of the wall modules so that I can pack them separately. The reason I do this is once geometry is packed, you can't easily apply and vary different materials to different parts of the packed geometry. So I pack them all separately and then pack them again. So now each wall is one packed primitive, you can see by those points. But if I want later, if I unpack them just once, then it separates out all these materials, but doesn't unpack it fully. So I kind of get the best of both worlds by still packing the geometry, but packing the materials separately. So the packed geo is coming in this stream, and this stream has either the input curve or the input blockout. This for loop is going to loop over each input curve or each piece of the input blockout and place the modules accordingly. Everything here is just applying the scale or flipping the geometry. So here, the explicit scale is applied if that option is checked. This flips the geometry if the option's checked. And then this scales to the target height or scales to the blockout height. And so the reason this is inside the loop is because to scale to the blockout height, it needs to change that each iteration so that it matches each piece of the blockout correctly. So this chain node takes care of the bulk of the work, which is placing the modules along the curve. And it looks like I have the invisible B-box check on. So let me uncheck that so we can actually see what's going on. So here are all the bounding boxes placed with the chain node. And then I just inject the actual geometry at the end. And the reason I place the bounding boxes first and then the actual geometry is to make these line up right. Okay, these pillars look kind of silly, so let me make them the same size. So the reason we place the bounding boxes and then inject the actual modules is so that they get aligned right. Because if we place the actual modules from the start instead of the bounding boxes, so if I plug this into the chain node, you'll see that the chain node is aligning the edge of each module, which is actually the edge of this pillar, to the next one. So we want it to align the bounding boxes to each other so that the pillars will each intersect the next wall by a bit. And then at the bottom here, there's just an option to either keep the modules packed as they are, or like I was describing earlier, unpack them one level so that all the materials are packed separately. So the last thing to talk about here is just how the system handles the blockout case. And it's actually quite simple. I basically take the blockout, so let me switch to the blockout input. So it basically just takes the blockout and converts it to curves so that it can process everything the exact same way. And the way I do that is I loop over each connected piece, I extract the height from the blockout and save that as an attribute, and then I use the lab split prim by normal to extract only the bottom faces from the blockout. So it grabs these faces right here because I have it set to grab the primitives facing the negative y direction. Then I use the extract borders node to get just an outline, which simplifies the geometry a bit. Without that, I have all these extra lines, which is not good for the next node, which is the lab's straight skeleton 2D. So what this node does is it extracts a skeleton from a 2D shape, but it doesn't behave well with these extra lines. Here is the skeleton that gets extracted. You can see that if I disable this extract borders, then it just errors out. But once I've done that, then I pretty much have the blockout again, but as input curves with the height attribute, and then this height attribute gets read by this transform if the user selects the match blockout height option. So that's how the Aqueduct generator works, and that pretty much wraps up the video. There's just one more thing I want to point out about material assignments. So in my actual scene setup, here are the Aqueducts. And of course, if you were to use this tool, you could shade your modules however you wanted. But I just generate a very simple noise texture in cops. So all my little shading cop nets, for the most part, are over here. And if I dive into the wall shading, just take a peek at this really quickly. Basically, I have some big rough patches of color as well as some grit, and I composite them together just to create like a little bit of interest. And similar kind of thing for a roughness map and a displacement map. I generate a couple different variations of that texture and assign them each to different UDIMs so that I can vary the textures by just varying the UDIMs on the walls. And you'll remember the walls were just auto laid out. It doesn't really matter at all how the UVs are oriented. So another way that I get a little more variation is in here, I randomly flip and rotate the different UVs of different walls just to like flip around the textures and get some variation. Of course, you probably don't want to do your materials like this is a very like quick and dirty way for me to just get a passable render. But since the walls are UV'd, you could apply whatever materials you want. This is just how I do it. And also I make sure to unpack these because the textures don't work well on packed geometry. I do the material assignment itself in LOP so I can change it on the fly, but this covers how I generate all the textures, all the models, the UVs, everything. So that's this video on the walls and the aqueducts. And in the next video, I'm going to be diving into how I create the towers. Thanks for watching.